Okay, welcome. Let's get started. So this class is going to be about graph theory. But before we get started, course announcements. Problem set 2 will be due on October 9th, not on October 2nd. It will come out in a few days. In the meantime, Vincent will have an optional list of practice problems, which will be available soon on Slack. We can give you feedback on your solutions, but they will not count towards a grade. Are there any questions about the course? Okay. When will PSET 2 be released? In a couple of days, not exactly sure. Okay, let's get started out with graph theory. What is a graph? So a graph is defined by two things, a set of vertices and a set of edges. The edges are unordered pairs of vertices. So they're unordered pairs from the set of vertices. Vertices are also called nodes. Often there is a cultural difference, like if it's a more math or theory-oriented setting, then they're called vertices. And if it's more applied, then they're often called nodes. We're going to use vertices, but feel free to use nodes. Yeah. An example of a graph. Here's a set of vertices, V1, V2, and V3, and an edge set, which is the set of just all possible pairs here, V1, V2, V1, V3, and V2, V3. Now you can represent this graph pictorially, and that's often done. It's important to remember that the graph is not the picture of the graph. The picture of the graph is just a way to represent it. For example, I could move around these blue dots, and that would not change the graph. The important thing is what is connected to what. There is no sense of location. So the graph just has three abstract things, which are called vertices, which are these three blue dots, and three abstract things, which are called edges. And the important thing is what is connected to what. There is no notion of sort of how to draw it. The drawing is just a way to visualize it. Okay. When do graphs show up? Basically everywhere. We're going to be seeing graphs throughout the rest of this course, but some particular applications are road networks or transport networks in general, when one's trying to see what is connected to what and how long it would take to get from one place to another place. So Google Maps runs based upon graph algorithms. Social networks, where there are where the nodes or vertices are people, and people are connected if they are connected in the social network. So there is an edge between two people if they are friends or something on a social network. There are these nice results about the diameter of graphs. So like how many degrees of separation are there in social networks? And that can be translated over to graph theory or just other properties of social networks. Facebook uses graphs a lot, for example. Electrical grids. In electrical grids, the particular what's called buses, so the sort of junctures in the network, correspond to vertices. And there is a physical network of wires connecting these buses. And there are various properties of the wires. So the edges in the graph actually have additional information. And there was a question asked. In some of these cases, yes, you have more than just the graph. You have node, vertex, or edge annotations. And so what that means is basically that each edge might come with some information about it, or each vertex might come with some information about it. For example, in a road network, locations are actually important. Though it's possible that you could get away without the full locations, that you might just need the lengths of the edges. In an electrical grid, you might be able to just deal with the impedances of the individual wires in the network. Another application is in chemical structures. So chemical structures are often represented, in organic molecules, they're represented by carbon skeletons often, which is the connectivity of the different carbon atoms in the molecule. And that is actually something which can be the input, for example, to a machine learning algorithm to learn properties of different chemical compounds. Or if you're working with proteins and protein folding, then there can be different graphs involved as well. Relationships between concepts. So there are things like knowledge graphs, which capture different kinds of relationships between concepts. And again, this is a situation where the edges in the graph contain extra information. So an edge might not just be what is connected to what, it might also be how it is connected to what. So the edges might have different types. You can imagine this, we're not really going to talk about coloring graphs, but you could imagine this as an edge coloring of a graph, where different edges have different colors associated with different kinds of relationship. So this could be, these two vertices in the graph, the knowledge graph, are connected because they are people and one is related to the other, for example. One as a parent-child relationship or something like that. There's a question about the vertices being in different planes. I'm not sure I understand what that question is. Would you like to clarify a bit more? And needless to say, there are a lot of other applications of graphs. I will come back to that question if you want to elucidate that a bit more, but let's move on for the moment. Okay, so let's take a look at some special graphs that will turn up a lot. Paths and cycles. Firstly, the path graph. It's kind of hard to say, path graph. The path graph is going to have n vertices. And if it has n vertices, then it has n minus 1 edges. The vertices, you can just label them 1 through n. The edges connect each vertex with the next vertex in the line. So these are some pictures of the first few path graphs. P1 has just 1 vertex and no edges. P2 has 2 vertices and 1 edge between them, and so on. Really simple. The cycle graph is very similar to the path graph, except it loops back on itself. You have all of these vertices, and then the final vertex is connected to the first one. So you can write that in this way, saying that Vi is connected to Vi plus 1 modulo n, for I is 1, 2, 3, so. And that just means that if you ever had V sub n plus 1 in this definition, V sub n plus 1 would just mean V1. It's just a convenient way of using modular arithmetic to write that things cycle back. Okay, so those are the two definitions of very simple graphs. Any questions at this point? Does Cn always contain Pn? Yes, Cn is always the same as Pn plus an additional edge. Good question. Okay, so some more definitions. We say a vertex V is adjacent to a vertex W if VW is an edge. That's just another way of saying that there is an edge between V and W. They're adjacent. We can also use the word neighbor and so to say that W is a neighbor of V. And you can talk about the neighborhood of V to be the set of all W that are adjacent to V. Cool. Lots of metaphors in graph theory. Like, I'm not going to go into most of the metaphors, but there's everything from neighborhood to there's a cactus graph, there's a caterpillar graph. I spent one summer when I was in college researching a graph called the claw because it looks kind of like a claw. Another piece of notation, we say the edge E between V and W is incident to the vertices V and W. So two vertices are adjacent, and the edge between them is incident to each of those vertices. So the number of edges incident to V, or alternatively the number of vertices which are adjacent to V, is called the degree of V. Just how many edges. As an example, the neighborhood of B is ADE. And how many vertices are in the neighborhood? Well, there are 3, so the degree of B is 3. 1, 2, 3. The degree of D, on the other hand, is 4. 1, 2, 3, 4. Cool. Problem. What is the sum of the degrees in a graph with n vertices and m edges? All the degrees of all the vertices. Seeing some consensus here. Let's take a look at an example. So in this example, we have n equals 5 vertices, and m equals 7, so 7 edges. The degrees of A, B, C, D, E in order are 3, 3, 2, 4, 2. Okay. If we sum them up, the sum is 14. You might notice that 14 is 2 times m. So why is this equal to 2 times m? Yeah, if you're counting, if you're summing up these degrees, each one of them is, each edge is going to contribute to 2 different degrees. So this edge, for example, adds 1 to the degree of A, it adds 1 to the degree of B. This edge adds 1 to the degree of C, adds 1 to the degree of D. So if you count up the edges, each one will contribute 2 to the sum of degrees. And so the overall sum of degrees is going to be 2 times the number of edges. This is a very simple fact, but it is important, and it turns up quite a bit. It'll actually turn up later. Okay. Here's another definition. A connected graph is one where you can get from any vertex to any other vertex by a path of edges. For example, this is a connected graph. You can get from any vertex to any other vertex. This is an example of a disconnected graph. In fact, there are 3 what's called components of this graph. Connected components. This is one connected component. It's just a single isolated vertex. This is a component with 5 vertices, and this is a component with 4 vertices. Okay. Another special graph, trees. So a tree is any connected graph that does not contain a cycle within it. Remember, a cycle is something that loops back on itself. This is a tree. You can see there are no cycles. You can, one way to think about not containing a cycle is that there is a unique path between any 2 vertices. Since it's a connected graph, there is a path between any 2 vertices. Since it is a tree, there is exactly one path between those 2 vertices. So for example, from here to here, you go. If there were 2 possible paths, then you would end up having a cycle somewhere. This is an example of something that's not a tree. It's called a forest. If you've heard of a random forest algorithm, then random forest is because of these kinds of things. So it is a collection of trees. So it is a disconnected graph. That's why it's not a tree. A collection of trees, which are individual components, disconnectedly of a graph, is called a forest. Remember, graph theorists, we like our metaphors. Okay. Now this is another example of something that's not a tree. This is not a tree because it has a cycle. Here's a cycle. It's a 5 vertex cycle. And again, this would mean that there are 2 paths, at least between two vertices, or some of the two vertices. So for example, here you could go this way, but you could also go this way. You can see my cursor, right, all of you? Okay, good. Thanks. I just realized it would be really bad if my cursor were not visible in the screen share. Okay, so this is a tree. Paths are also trees, each one of these paths, because it doesn't have any cycles in it. Okay. So trees can be very simple. They could just be like the trunk of the tree, basically. How many edges does a tree with n vertices have? I'm seeing a lot of n minus 1. What's a way we can try to prove it? So intuitively, if there's more than n minus 1, there will be a cycle. It's hard to make that completely rigorous. Yeah, it's hard to jump from that to, like, that is correct. That is, yes. If you added another edge to a tree, in fact, if you, in any situation where you have a tree and you add another edge to it, if you don't add another vertex, then you have to create a cycle. So let's see if there's a way to prove this. I'm seeing some suggestions of induction. Let's try induction. Let's assume that every tree with k vertices has k minus 1 edges. What about a tree with k plus 1 vertices? What can we do? We have a tree with k plus 1 vertices. How can we use our assumption to show that that it has to have k edges? I'm seeing some suggestions of adding vertices to our smaller trees, but we don't necessarily know that there's a way to add a vertex to a smaller tree to create t. All we have is t. Okay, we can remove a vertex from t. Great. Let's try cutting off a vertex. Which one? So I'm hearing some suggestions of a vertex of degree 1, which is called a leaf. What about a vertex of degree 1? Since then we would cut down the number of edges by 1, 2. So this is, for example, a leaf. It's a vertex of degree 1. If we cut this off, we kill one vertex and we kill one edge. The new graph is connected because we cut off a vertex of degree 1, and it can't have any cycles because there weren't any cycles in t. So it's still a tree. We've trimmed the tree, as it were. Therefore, it has k minus 1 edges because it has k vertices. So it has k minus 1 edges by our inductive hypothesis. So that meant that t must have k edges because we took one away to get this trimmed tree. And we're done, right? So what's missing here? And correct, if we just tried going the other way, adding a vertex to a smaller tree, we wouldn't necessarily get all of the trees with k+1 vertices. We would actually, but it's not immediately clear that we would. We'd have to prove that. Okay, so there are two issues actually. A couple of things are missing. First, we need a base case for the induction. That's always important for induction. It's sort of a thing. I don't think someone's going to gloss over it, but in this case, let's just do the base case for the induction. Whenever you're writing a formal proof, you have to have that. Just sometimes I will not go into it in detail. But here, if k equals 1, then only one tree has one vertex and 0 edges. It's just a single vertex. That works. But there's something more subtle. We also assumed that T has a degree 1 vertex. We assumed that it has a leaf. Why is there some degree 1 vertex? This is I'm sorry for harping on the details of a proof like this. I realize this is an intuitively obvious proof, but if you're writing a proof like this, you have to go through all the details and getting into the habit of making sure that when you say take a degree 1 vertex, you also immediately think, wait, what if there isn't a degree 1 vertex? Is really important. Yeah, so we will have to use the fact that T is a tree. Otherwise, we never actually used really the tree property here. So we're going to have to use the tree property in some way. Let's try taking a walk in the tree T, each time going to a vertex we haven't visited before. We could do this by contradiction, but we don't actually have to do the contradiction. So let's try taking a walk. We'll have to stop eventually at some vertex V with no more new vertices to go. And just taking a walk here, I'm just going to, eventually I'm going to stop somewhere, right? I'm never allowed to, I'm not allowed to go back to any vertex that I've visited before. Why does this vertex that I stop at have degree 1? I really like the pun of you got there and you can't leaf. So there has to be a leaf. That is true. It is an excellent pun proof. So yeah, any other edges from V would have to circle back to vertices we've already gone to, which would give us a cycle. So V has to have degree 1, so we can take it away and do our induction. Okay, now we're fully rigorous. We have a good proof. Cool. Degree 1 vertices in a tree are called leaves. Yeah, and there is always at least one leaf in a tree. Actually, there are always at least 2 leaves in a tree. A path has 2 leaves. That has the minimal number of leaves. Unless the tree has only 1 vertex, in which case there's only 1 leaf. Well, I guess there are no leaves in that case. Okay, more special graphs. Complete and empty graphs. The complete graph has n vertices and all the possible edges between them. For example, here there are 2 vertices connected, 3, 4, 5, 6, 7. Complete graphs are generally called K sub n. How many edges does Kn have? In answer to the question, you do not have to prove any property that is proven in class. You can just cite it on the problem sets. Just say as we proved in lecture or something like that. Cool. So yeah, we have the binomial coefficient, as we just recently saw. N choose 2, because you have to pick 2 different vertices to have an edge. N choose 2 is just n times n minus 1 over 2 edges. Great, that's the number of edges in a complete graph. There's also an empty graph, which is what's called the complement of the complete graph. So complement graph is wherever you had an edge before, there's now no edge. Wherever you didn't have an edge before, there now is an edge. So if you started out with all the possible edges, the complement of that is none of the edges, and that's the empty graph. And there are boxes around here just to make it clear that there is a graph here, it's just there aren't any edges in this graph. It's a perfectly legal graph, and there is an empty graph for every number of vertices. So this is a 5-vertex empty graph. So some more definitions. A clique within a graph is a subset of the vertices that form a complete graph, i.e. they have all the possible edges. So here are 2 clicks. This is a graph with one click in red, and here is the same graph with another click in red, and these are 2 actually overlapping clicks. This edge would itself also be a click. It would be a 2-vertex click. An independent set within a graph is a subset of the vertices that form an empty graph, i.e. there are no edges between them. So for example, here we have 3 red vertices, which none of them, no pair of them is connected by an edge. So that is an empty, that's an independent set. Likewise, these 3, likewise, these 4, and likewise, these 5. No edges between any pair of those vertices. This is a graph which you may or may not see again, but it's a really interesting graph for graph theory. It's called the Petersen graph. Petersen with a E-N at the end. And one of the cool things about it is that it is symmetric, so that every vertex is the same as is equivalent to any other vertex. In that each vertex, from each vertex, it looks the same. Now I realize that the way you draw it, it doesn't look the same, but if you calculate it out, you can see each vertex has degree 3. It's adjacent to 3 other vertices, and the pattern of adjacency is the same with respect to each of the vertices. This turns out to be extremely important for a bunch of graph theory situations. This is called a wheel graph because it has it's a cycle with a central vertex that's connected to everything. And we'll get to this in a moment. Yeah, independent sets also come up if you're talking about graph coloring. This is just a side note. Graph coloring one of the ways to do graph coloring is to color the vertices of a graph so that no 2, in some number of colors, so that no 2 adjacent vertices are the same color. If you do that, then each color class, so the set of vertices that are red, the set of vertices that are blue, have to be independent sets. So you're trying to partition the graph into independent sets. What's called the chromatic number, this is a side note, so you don't have to remember this. The chromatic number of a graph is the minimum number of colors you need to color the graph so that no 2 adjacent vertices are the same color. So for example, we could color this in, I guess it would be 4 different colors. So here, red, 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 blue, 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 green, and purple. I think the chromatic number of this is actually 4. You cannot do it with fewer colors, but yeah, you're partitioning it into independent sets. If you didn't get that, don't worry. But that's just a side note about chromatic numbers, which are extremely important. And not just in graph theory, they're also extremely important in something called discrete geometry, which is the study of things like polytopes, which will turn up later when we talk about linear programming. So chromatic numbers are one of these things that just turn up throughout mathematics. Bipartite graphs. A bipartite graph is a graph that can be divided into 2 groups of vertices, with all the edges going between groups instead of within groups. So these are some examples of bipartite graphs. Often we write bipartite graphs in such a way that they're all on one side in one part and all on the other side in the other part. And sometimes you just you color them in such a way so that you can so these are separate color classes. So these are all red, these are all black. These are the 2 different parts. All red, all black, 2 different parts. No edges between within the individual parts. Another way to say that is that each part is an independent set. You can divide it into 2 independent sets. Here, this is the red things are an independent set. The black things are also an independent set. Are there any questions? Okay, so yeah, bipartite graphs, if you were following the discussion about chromatic numbers, they're just graphs with chromatic number 2. A complete bipartite graph has all the possible edges between the 2 groups of vertices. So here are the red vertices, here are the blue vertices. Since it's a bipartite graph, no edges are within the red vertices, no edges are within the blue vertices. They're all between red and blue. And since it's a complete bipartite graph, every possible red-blue edge is there. What is the maximum number of edges in a bipartite graph with n vertices? Suppose that n is even. All possible ways to divide them into parts and add edges. So let's prove this. Say there are n1 vertices in one part and n2 vertices in the other part. We definitely will want all the possible edges. So it should be a complete bipartite graph. So there are n1 times n2 edges, every possible pair. Now, but what are n1 and n2? We don't know what the right way to partition them is, right? Like, we don't know whether they should be like all but one over here and then one over here, or half and half, or yeah, whatever. So how do we do this? What's a way to prove it? Aha, yes. We can use the AMGM inequality. By the AMGM inequality, we know that the square root of n1, n2 is less than or equal to n1 plus n2 over 2. And we know that n1 plus n2 is just the full number of vertices, which is n. So square root of n1, n2 is less than or equal to n over 2. And equality happens exactly when n1 is equal to n2 is equal to n over 2. So this is attainable. Therefore, the maximum number of edges is just, if you square this, n squared over 4. Cool. Okay. Prove the connected graph is bipartite if and only if it doesn't have any odd length cycles. An odd length cycle would be, for example, C3, which is a triangle, or C5, which looks like a pentagon. So an if and only if proof. And I realize we haven't really talked about these. So this is sort of an introduction to if and only if proofs. An if and only if proof means going two different directions. If A is true, if and only if B is true. There are two things that you need to do. If A is true, then B is true. And if B is true, then A is true. Just proving one of them is not enough. Consider the statement, something is a human if and only if it is Abraham Lincoln. It is true that if something is Abraham Lincoln, then it is a human. However, it is not true that if something is a human, then it is Abraham Lincoln. The if and only if means that you have to show both implications. So let's do direction one. Suppose that the graph G is bipartite. We must prove it doesn't have any odd length cycles. This is the first direction. What do we do? Yeah, so this is basically a contradiction proof, though we don't really have to phrase it as a contradiction proof. Let's consider some cycle, and we're going to prove it's not odd length. Okay. So the vertices of the cycle have to alternate between parts 1 and 2. Why is that the case? Well, the only edges are between parts 1 and 2, and we know that each consecutive vertices in the cycle are connected by an edge. So as you take an edge, you have to switch between parts 1 and 2, or vice versa. But if the vertices are alternating, 1, 2, 1, 2, 1, 2, 1, 2, that means that it's going to have even length. Done. Okay. There is a question. Can't we show that for any odd length cycle in a bipartite graph, if we try coloring the vertices, we won't be able? Yes, that is another way to do this. That is another way to write down what is essentially the same argument. Absolutely. Okay, so that was direction 1. We showed that if a graph is bipartite, then it doesn't have any odd length cycles. Direction 2. Suppose that the graph doesn't have any odd length cycles. Now let's prove that it's bipartite. How can we do this? How would you go about trying to show that something is bipartite? Suppose you were just working with an example. Yeah, exactly. Put the vertices in 2 bins. Something's bipartite if you can color the vertices red and blue so that no 2 red vertices are connected, no 2 blue vertices are connected. So go through the graph 1 vertex at a time, picking which part to put each new vertex in. If we pick a vertex that's connected to vertices we already have, then what do? We're clearly going to have to try to put it in the other bin, the other color. If it's connected to some red things, then we make it blue. If it's connected to some blue things, then we make it red. When do we have a problem with this approach? Yeah, so if we picked a new vertex, and it's connected to both vertices in parts 1 and 2. So we already had vertices that were colored red and vertices that were colored blue, and we add a new vertex. We can't make it red because it's connected to a red vertex. But we also can't make it blue because it's connected to a blue vertex. Can this happen? We are gradually building up this bipartite graph, and suddenly we get a contradiction. We have something that's connected to both sides of the bipartite graph. We can go back and look at some bipartite graphs. Here's a bipartite graph. Suppose we have something else that's connected to both sides. Ah, yes, this would make an odd length cycle. That's because this graph is connected, so if you follow these edges around, you're eventually going to come back. And if you come back, then it will have to be an odd length because everything else is alternating, and the only thing that is out is the new vertex. Adding a vertex with 2 edges to a connected graph is going to generate a cycle. We knew that because of what we were doing with trees, right? If we have any connected graph and we add a new vertex with 2 edges to it, it's going to have to generate a cycle. And if the edges go to parts 1 and 2, then it would have to be an odd cycle. Are there any questions about this? do we need to explicitly handle leaf nodes, which would not show up in cycles? I don't think that you need to explicitly handle leaf nodes because a leaf node wouldn't lead to such a contradiction. If it's only connected to one vertex, then it will not be connected to vertices in both parts 1 and 2, and you can just color it. It will never be such a problem vertex. We're dealing with this in the situation that we did run into a problem vertex. If you don't run into a problem vertex, then you're fine. This is not a formal proof, but it should give you enough information that you can just write down the formal proof. Okay, let's get to Königsberg. So in Königsberg, which is now called Kaliningrad, and there's a story behind that, and I'll tell you about that at the end. There are some bridges shown below, or at least there were several centuries ago. Is it possible to cross over all of them in some order without crossing any bridge more than once? Whoops. Okay. I like the suggestion of swimming. I think that would be deemed cheating. Okay, this exact layout, yes, this exact layout of bridges. This was the real layout of bridges, for what it's worth. This was actually a problem that some real people had, and they were like, huh, I wonder if it's possible to do that. So we can turn this picture into a graph. Putting every piece of land as a vertex of this graph, A, B, C, D. There are 4 vertices. Now, this is a kind of graph that we haven't seen before. It's what's called a multigraph, where several edges can exist between the same pair of vertices. Multigraphs are basically the same as graphs. Like everything that we've discussed will basically carry over nicely to multigraphs. We'll come back to this in a moment. But let's first frame this problem, and then we can solve a more general problem. We want a path through this graph that traverses each one of these edges exactly once. Like ding, 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 ding. And then you want to jump over to here. Okay. It doesn't seem very doable. People in the chat do not seem to think this is doable. So these are called Eulerian paths. And you can ask the general question, when does a connected graph or a multigraph have a path that traverses each of the edges exactly once? Such a path is called an Eulerian path, named after the mathematician Leonhard Euler. So Euler was there in Königsberg, according to the story, and people asked him this question. They were like, we've been trying to get around all the bridges because this is like a challenge in Königsberg, and we've been trying to do it. Can we do it? And Euler was like, no, and this is a proof. Yeah, definitely. That's a pretty cool challenge for if your city is like, can you get across all the bridges? At least that's the story. Okay, so let's try to solve the general problem. When is there an Eulerian path? Here's an example of one. Here's this other graph, which is not Königsberg. In this case, we can have an Eulerian path as just A, C, D, E, B. And then we need these 3 edges. So we could do back to D, A again, and then back to B. So here, ding, 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 ding. That covers all of the edges. Okay, yes. Yes, I like the analogy to a pub crawl. This is like really, like there are pubs on all the bridges and you want to do it in the most efficient way possible. Okay. So before I state the theorem, are there any ideas as to what the theorem is, if you didn't see it? It's not obvious. So if you have a bipartite graph, this is not actually enough. For example, if you had if your bipartite graph were just, this is the claw, so 3 edges coming out of one vertex, you couldn't go across all the bridges because you could at most do 2 of them. You couldn't get the 3rd one. This isn't provable in linear time. Yes, it is. It is solvable in linear time. There's a different path, a different problem called Hamiltonian paths, which is an NP-complete problem, or believed to be. Okay, so the theorem is that if and only if you have at most 2 vertices with odd degree, then there is an Eulerian path. So in this particular case, the number of vertices of odd degree is 3, 3, 2, 4, 2. So there are only 2 vertices with odd degree, so we're good. If you had 3 vertices of odd degree or 4 vertices of odd degree, that would be bad. Okay, it's a bit of a random condition. Why is that the case? So this is an if and only if problem. So how should we prove an if and only if problem? Yeah, both directions. Okay, so let's do both directions. First, let's suppose that the graph has an Eulerian path. Why should it have at most 2 vertices of odd degree? You're going to, again, remember this one, which is like ding, 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 ding. Ah, yes. So each time a vertex occurs in the path, it adds 2 to its degree unless the vertex is at the start or the end. Each time we enter a vertex, we have to leave it unless it's the first vertex or the last vertex in the path. That means that every vertex in the middle of the path is going to have even degree. Because each time we go through it, it just adds 2 to the degree. The only things which get ended up with odd degree are the first and the last one. Okay. Starting and ending vertices have odd degree unless they're the same vertex, in which case there are no vertices at all with odd degree. That's called an Eulerian circuit. Okay. So that was maybe the easier direction? They're neither of them that hard once you know what it is. Okay. Now suppose the graph has at most 2 vertices of odd degree. We're going to do this is the other direction. We'd like to show that there is an Eulerian path or circuit. Let's divide into cases to make it a little bit easier. How many vertices with odd degree could there be? We were talking about 2 or 0. Could there be 1? Why couldn't there be just 1 vertex with odd degree? Aha! Yes, so the sum of the degrees is even. Remember, it turns up in places where you wouldn't expect it. The sum of the degrees is even, so because it's twice the number of edges in the graph. So the number of odd degree vertices has to be even. So there has to be only 0 or 2. There couldn't be just one odd degree vertex. Okay. So there are two cases, 0 or 2 vertices of odd degree. Let's do 2 vertices of odd degree, v1 and v2. Let's do induction. There are different ways of doing this. There is an explicit algorithm, which I encourage you to look up if you're curious, and it can do it really fast. And the algorithm that we're doing here is not the fastest one. It's sort of like we're sort of describing an algorithm for it, but it's not the fastest one. Unless the graph has just 2 vertices, so one of these 2 vertices, one of v1 and v2, has to be connected to some other vertex w, right? Like, unless these are literally the only 2 vertices in the graph, there's some other vertex out there, and that has to be, since it's connected, it has to be connected to either v1 or v. It has to be something connected to v1 or v2. Suppose without loss of generality, like v1 is connected to w. So w, since it's not v1 or v2, we know it has to have even degree. So what can we do? Remember, we're proceeding by induction here. What vertex can we remove? Following up on the suggestion. Or what could we remove? Aha, yes. So we can take out an edge. We're doing induction on the number of edges. What if we take out that edge? Well, we knew that v1 started out with odd degree, and w started out with even degree. So we've switched out. v1 now has even degree. W now has odd degree. So we still have 2 vertices with odd degree, and we have another connected graph. That means that by induction, there is an Eulerian path between w and v2, which are the 2 vertices of odd degree, and we can just add v1 w onto it. Done. We have to do a base case if we're being careful, but I'm going to skip the base case. It's just a very simple graph. Just P2, the simple graph there. Okay, case 2. No vertices of odd degree. In this case, let's do basically the same thing. Let's take out some edge that doesn't disconnect the graph. So for example, if it's tree, we can just take a leaf edge, but anything, we can just take out any edge that doesn't disconnect the graph. In that case, we're going to get a connected graph with 2 vertices of odd degree. And what can we do then? Yeah, go back to case 1. Using case 1, we got an Eulerian path. We can add the edge back in to complete an Eulerian path, which is actually an Eulerian circuit on the full graph. Okay, so now let's go back to Königsberg. In Königsberg, we had this particular graph. Can we do it? No, we can't do it. All 4 vertices in this graph have odd degree, so it really sucks. They really didn't design the bridges very well. Okay, so that is it for today. Next time we will be doing linear algebra 1.